Welcome to the Virtual Chem Labs Explainer series. Look, if you're just stepping into the wild world of computational chemistry, our goal today is actually pretty simple, but it's super powerful. We want to help you confidently plan your calculations right from the get-go by really understanding that delicate balance between accuracy and computational cost. So, welcome to this explainer on Gaussian 16. Brought to you by Virtual Chem Labs. You are absolutely in expert hands today. I'm your enthusiastic guide, and we're going to break down exactly what Gaussian is, and more importantly, what it can calculate for you. We're building a rock-solid foundation for your future research.
Okay, let's dive right into this. To build a really clear mental map of this software, we're going to follow a precise agenda. First, what is Gaussian 16? Second, core calculation types. Third, the 4 inputs that control results. And fourth, a practical properties checklist.
All right. Section 1. What is Gaussian 16? Computing electronic structure. At its core, Gaussian is a quantum chemistry package that uses some pretty sophisticated quantum mechanical models to estimate how electrons are distributed in a molecule. And, how that specific distribution determines molecular energy, physical structure, and all those observable properties. But hey, here's a critical reality check. Gaussian doesn't automatically understand the chemistry on its own. It's a brilliant tool, sure, but it's fundamentally just an engine waiting for your instructions. You literally have to tell it exactly what to do by providing the molecular structure, the method, the basis set, and the specific job type. Now, what's really interesting about this is the highly logical input-to-output pipeline. This forms the absolute beating heart of every single workflow you'll do. You start with a molecule, apply a method plus a basis set, define the calculation type, and boom, out come your properties. Grasping this flow, that is the ultimate key to mastering Gaussian. Moving on to Section 2, what can Gaussian calculate? The core calculation types. First up is the single-point energy, or SP calculation. This calculates the energy of a molecule at a fixed, unchanging geometry. Think of it like snapping a quick photograph. It's frozen in time. It is incredibly useful for comparing different conformers, evaluating reaction energies, or just refining your energy numbers on structures you've already optimized at a lower, cheaper level of theory. Next up is the geometry optimization, or OPT. This searches for a low-energy structure, usually a stable minimum. So, if a single point is a snapshot, an optimization is more like a journey down into a valley. This is your absolute workhorse calculation. I mean, you almost always need to run this to get realistic, stable geometries before you even try to predict any other properties. Then we have the frequency analysis, or FREC. This calculation does 2 massive jobs for you. First, it computes vital thermochemistry data, giving you zero-point energies and Gibbs free energy under standard assumptions. Second, and honestly, just as importantly, it verifies if the structure you just optimized is truly a stable minimum. So the crucial point is this simple binary rule. If you see exactly 0 imaginary frequencies in your output, awesome, you have a stable minimum. But if you have exactly 1 imaginary frequency, that almost always indicates you found a transition state. You can instantly diagnose the state of your molecule just by glancing at these results. Pretty neat, right? And Gaussian goes way beyond just the basics too. It can actively locate really complex transition states and compute activation barriers. It supports continuum solvation models to approximate how a solvent environment is going to affect your energies. And it can even model excited states to help you predict UV-Vis transitions and related spectroscopy. All right, Section 3, the 4 inputs that control results, balancing accuracy and computational cost. Input number 1 is your molecular specification. You absolutely must flawlessly define the exact starting geometry, the total charge, and the spin state, which is also known as multiplicity. Because, think about it, getting the charge or multiplicity wrong won't just give you a slightly off number. It will completely alter the electronic structure and the actual chemistry that Gaussian calculates. It's literally a totally different molecule at that point. And this brilliantly illustrates input 2, the method. Whether you choose Hartree-Fock, density functional theory, DFT, MP2 perturbation, or a coupled cluster approach, this completely dictates the specific quantum model you're using. You are fundamentally trading off extreme accuracy for computational cost. You just have to pick the right mathematical tool for this specific job. Let's move to input number 3 and see how this actually builds on your method, the basis set. This is the mathematical description of your orbitals.
Larger, more flexible basis sets generally improve your accuracy because they give the electrons way more mathematical room to behave realistically. But the catch? They dramatically increase the calculation time required.
Finally, input 4, job type and technical settings. Choosing whether you're running an SP, opt, or FREC job, paired with highly technical settings like self-consistent field, or SCF, convergence grids, that strongly dictates your overall runtime and the actual mathematical stability of the calculation itself.
Which brings us to Section 4. What properties can you report? The Practical Properties Checklist.
From your successful runs, you can pull a ton of great data. We're talking your optimized geometry, total electronic energy, and relative energy changes. You can report vibrational frequencies, IR intensities, and complete thermochemistry like enthalpy and Gibbs free energy. You can pull dipole moments, atomic charges, UV-vis transitions, reaction barriers, and solvent-corrected properties. Just remember the absolute golden rule of verification here. You must always pair these reported results with the exact method and basis set you used. Period.
So, where are we heading next? Well, in this explainer, we covered what Gaussian is. Next up in this roadmap, we're going to tackle basis sets in depth. Later, we'll dive into methods, and in the future, we'll walk right through your very first calculations. We're building your decision framework step by step so you are never just guessing.
A massive thank you to VirtualChem Labs for powering this foundational knowledge. I highly encourage you to go visit virtualchemlabs.com to check out their incredible workshops and learning resources. So, looking at this vast landscape of quantum capability, how will you utilize your new mental map of computational chemistry to accelerate your own unique research? Think about it. See you in the next explainer.